Hi, welcome to StrathSEDS Preliminary Design Review presentation. My name is Neve, I'm the team lead for this project, and if you have any questions about the PDR that you'd like answered, you can reach out to me at neve@strathseds.org. I'll make sure to get back to you. So I thought I'd start off with introducing the leadership team for this project. So we have myself, like I said, team lead. We also have Matthew, who's our treasurer and procurement specialist, Kyle, who's leading our coding team, Jakob's leading our electrical team, and Pablo's leading our mechanical team. And you'll hear from most of these guys later in the presentation. So jumping straight in with our project mission statement, our primary mission is to deploy 4 solar panels from our payload using a hold time release mechanism, and this will hopefully extend the lifespan of our payload. We also hope to validate the operation and performance of these solar panels, which should prove that our concept works. Our secondary mission is going to be to gather data on ascent and descent profiles of both our CANSAT and our launch vehicle. So we'll be gathering pressure and GPS data, and this should help with future society projects, so that next time we build a rocket, next time we build a payload, we have all that information to build on. And we'll also be live streaming telemetry data from the launch to our Twitch channel like we did last year, and this is to help out with a couple of outreach projects we have going on at the moment. So just to give you a quick overview of the concepts of our mission, so obviously step 1 is preparation for launch. The launch vehicle will then ascend up to hopefully spot on 3 kilometers, but we'll see about that. The payload will then be ejected and the drogue chute will be deployed so that everything kind of descends at a reasonable rate. At around 600 meters, the main chute of the rocket will be deployed, and once the payload has landed, our solar panels will be deployed, and hopefully this will help self-rate the CANSAT, which should make it easier to communicate with as well. I'll now pass you over to Pablo, who's going to be going into a bit more depth on the design details of both our launch vehicle and our CANSAT.
With that said, let's get into some of the technical details. Here we see a cross-section diagram of our rocket CAD. We're starting from the left-hand side, we have the nose cone, which will be shot off when we reach apogee as a first deployment stage. Following that, we have the drogue parachute, which will be slowing us down during most of the descent. After that, we have the CANSAT in its payload bay. They're all folded up so it fits in the rocket. Next, we have the ejection piston, which will be used to make better use of the black powder explosion to actually drive it out of the rocket. And the avionics bay, which will be holding the rocket's brain, all its electronics, and the 2 ejection canisters to activate the separation events. Following that, we have the main chute, which will be deployed at the second ejection event. And beyond that, we have the motor, its 4 centering rings to keep it still, and through the wall fins that will be epoxied in place to give us a solid basis for the rocket. Looking into the recovery a bit more, we'll be using dual deployment as is required by the competition regulations. Our first separation will be of a drogue chute at apogee, which should slow us down to about 30 meters per second. And then later on, we'll deploy the main chute to slow down to 10 meters per second for landing. To allow this, we'll need to separate the rocket in 2 places. The first of these will be at the nose, as I mentioned before, which is where we'll be deploying all our payload. And the second, further back here, where the main chute is, to deploy at lower altitude. We've done some preliminary calculations on the required diameters for the parachutes, and you can see those here. Having looked at various different motors, we've come to the conclusion that the Pro 75 5-grain Cesaroni motor is what we'd like to use. Its high impulse gives us excellent apogee results using OpenRocket. These have been further refined using Brasero to better take into account sonic effects, as we'll be travelling quite close to the speed of sound. Those secondary simulations have given us an apogee of approximately 3,400 meters. Like any rocket, will be made out of multiple parts that all need manufactured in different ways. Many of the key parts are being made of molded fiberglass. This is a method that we've been practicing using 3D printed molds that are then filled with epoxy resin and fiberglass to create parts to our design specifications. And the larger fiberglass parts are being bought off the shelf, and those being mainly the body and coupler tubes. Several of the more detailed parts will be directly 3D printed, such as the PCB mounts and the deployable arms and related mechanisms for the CANSAT. There's a few metallic parts involved, including the retainer ring, several threaded rods, and other miscellaneous bits of hardware, which will mostly be off the shelf. Here we have a sketch of the mechanical structure of the CANSAT. There's CAD coming on the next slide, but it's not complete yet, so we're using this for now. You can see there are two bulkheads on the top and bottom. These will be transferred and flowed between the two of them, connected by 4 steel rods. Then we have the deployment arms, which are actuated by springs and held down by solenoids before released, so that we can actuate them whenever we need. And then you can see that the electronics will be mounted between these threaded rods in the central space that remains. So for the structural analysis we've done, there's been some calculations done to ensure that the deployment loads are not too great. We find the expected stresses to be well below the yield points of the steel rods that we're using, so we're quite confident with that. And we've done some calculations on the size of the parachutes that we'll be needing to bring the CANSAT down safely. We'll be using washers to distribute the loads from the rods onto the fiberglass bulkheads, and we'll be validating these assumptions using some drop tests up a nearby bridge. With that said, I'll be handing over to our electrical team to talk about avionics.
Okay, proceeding now on to avionics. According to the regulations of Mach-23, we have decided to incorporate a COTS avionics computer in addition to our own student research and developed computer. The COTS computer is in charge of recovery and all flight data. It also records attitude and GPS locations, so it's a completely separate system used for both recovery and for data logging, used for recording the altitude of the flight. Our own avionics system is going to be split into 3 boards this year. This is to simplify manufacturing. That means we can use a singular main board that's going to be used across the launch vehicle and the payload, as well as the ground station, and a peripheral, or in this case a payload daughter board, is going to be used on those specific systems whenever an additional feature is required. So for the payload itself, the daughter board would include a controller, or rather a connector for the solar panel, and circuitry for measuring and dissipating the power. That means we can record and certify that our mission was either successful or not. And there's also an additional GPS board that allows us to position it at a different angle to the rest of the electronics, which would simplify and aid the operation of the GPS itself. And going over the student research board, here is a block diagram of what we're planning to use. This is including most of the features that the launch vehicle and payload requires. So a microcontroller, power control, sensors, which include an inertial measurement unit and an altimeter, and 2 redundant storage spaces. There's also communications, which I'll go over in later slides, and demonstration recovery electronics. We won't be using them, as I mentioned, it's not allowed in the regulations, but we will be trying to see if our deployment mechanisms fire at the same time as the COTS mechanisms, just to make sure that our own designs work as well. And there's also some simple interfaces and GPIOs to aid us in the development of the main board. We have acquired a full list of components. We are only working on the radio at the moment. The rest of the components are not necessarily set in stone, but those are the ones that we're going with the design for now. And it all centers around an STM32 microcontroller, same as we did last year. And the radio itself is a standard LoRa radio, which I'll go over in a second. And all the other components listed here will also have links in them in the presentation. The recovery system that we will be using first starts with our COTS computer. This is the Ectimer Quasar, and it is used to deploy the dual deploy parachute, and also has redundant position data that we'll be receiving on a separate receiver module. The receiving setup here is very simple and would be a receiving antenna, separate for the COTS computer and separate for our own, which would be receiving the data from both the launch vehicle and the payload, and would aid us in finding and recovering the payload and launch vehicle after the flight. The egg finder obviously would only be present on the launch vehicle, so we will be relying on our own ground station systems to recover the payload. And there's also an integrated buzzer or sound device on our main board. This is to aid in locating both in the field while we're looking for them. As far as the licensing goes for our telemetry, we are working on the same frequencies as the egg timer, but obviously we will be choosing separate channels to minimize any interference. Both devices should have automatic radio negotiating, so they shouldn't transmit on the same frequency. They're all operating under the same license, and which allows for airborne use, and both of them will share altitude and location data to maximize the chance of finding our launch vehicle and payload, but also our own telemetry will include the speed and the deployment status of our own recovery systems, battery information, and all the additional information that the COTS computer doesn't collect. And that's it for electronics.
Over to me now. We've included a risk and mitigation diagram here. We've included mostly things that are going to happen on the launch day and a little bit about the construction and testing process. That's going to be touched more upon by Neve later in the slides. We're required by the department to submit a lot of risk assessments for most of the procedures that we're going to do in the lab, and these are going to be written between PDR and CDR likely. We've also included a budgeting section. The overall project cost estimate right now is sitting at around £4,500. Most of this is towards the mechanical team and entry fee, specifically towards the motor. Mechanical costs have been broken down quite stringently here, as you can see. Electrical costs have been broken down by the team, but it would become really cluttered here, so we've given them their own specific overarching section. End costs are likely going to end up lower than what you see here. We've given them quite a big margin just for safety for planning at this point. Accommodation has also been accounted for in this budget. However, members who want their own warm bed are likely going to pay this themselves, as camping is a cheaper alternative. Our current society bank account, our budget, is sitting at roughly £3,150, give or take a few radio modules. This may be enough to afford the project. However, if it ends up running over, we can look into other sources like the University of Strathclyde Student Executive Funds to fund specific things like entry fees or other specific parts that we invoice them for.
Okay, so moving on to our project timeline. I was going to include the full Gantt chart here, but it's quite big and it was quite hard to read all the details on the slide, so I've attached it to the slides. So if you want to look at it in a timeline format, you can, but for now I've included the key dates that we've got. So we've got all of our deadlines here, which you'll obviously know about. In terms of admin, the key one for us has been the lab workshop inductions. So to use the inductions in our to use the labs in our university, we have to put everyone through an induction session. So we've actually been carrying those out last week, and they're all completed now. So the next step in terms of that is to make a full testing plan and have some more detailed risk assessments, because right now they're quite high levels. So we'd like to have more specific ones for each test that we want to do. And we've also got some time planned for travel logistics planning. We're hoping this won't take too long because we all live in Glasgow, and as far as we know, the bus will be leaving from Glasgow, so this should be pretty straightforward, but we have allocated time for it just in case. In terms of procurement, the deadlines that we kind of set ourselves is that we want our motor ordered by the 17th of February, all the rest of our mechanical components ordered by the CDR, and all of our electrical components ordered by the time you're hopefully watching this video, and we are on track for all of that right now. In terms of the launch vehicle and the CANSAT, we've completed the first iteration of both of the designs, so we're now working on the second design iteration. Something you might notice from this is that the CANSAT design is kind of lagging behind the launch vehicle. This is intentional because we've learned from the last 2 years that the launch vehicle is the most important part of the project. If that doesn't work out, then you have no payload to launch, so we've kind of tried to put a lot of focus on that so that we can start testing our launch vehicle earlier, but we should still have enough time to do both. We would plan for that. We've got testing deadlines and quality control, and we hope we've included everything. But yeah, again, you can look at this in Gantt chart form if that's easier. So to conclude our presentation, the next steps we've identified to get ourselves to the CDR level are completing the CAD models of the payload, so hopefully that will be done in the next couple of weeks. We'll be finalising the design of both the payload and launch vehicle, begin some prototype testing of key mechanisms so that we can make sure that our designs are actually possible. We'll also be creating a full testing plan and accompanying risk assessments in the coming weeks so that we can actually start testing. We'll have completed procurement for the full project by CDR, and as a final note, we'd like to acknowledge that this project's been fully funded by the Strathclyde Alumni Fund. It's really nice of them. It means that all of our funding started for this year, pretty much. So yeah, thank you very much for listening to our presentation. Like I said at the start, if you have any questions, you can reach out to me at neve@strathseds.org. Look forward to hearing from you soon with feedback.